All right, Algebra 1 notes. We will be covering section 9.1, properties of radicals. Radicals are like square roots, but there's other kinds of roots. Just put your name on your notes, and the date, and your period. General good practice in any class. Okay. So we're gonna do a little review. Like we talked about this a little bit back in chapter 6. So back in chapter 6, we did square roots. So we're gonna write down some common square roots and jog your memory. So square roots. So the square root of 1 is, what do you multiply times itself to get 1? 1. Right? Square means to multiply something times itself, right? Square root of 4 would be the next nice one. 4 is 2 times 2, 2 squared. The answer is 2. So square roots are asking, what would you square to get the number inside there? Square root of 9 is 3. Square root of 16, 4 times 4 is 16. Square root of 25 is 5. 5 squared gives you 25, so the square root is 5. So the square root's like undoing the squared. 36, 6 squared, square root is 6. And we can keep going, but we'll just stop there for right now. Cube roots. We're going to be encountering some cube roots. So cube roots, you're looking for a perfect cube, something that's cubed. And you write a little superscript 3 here. Now, you could write a superscript 2 here, but we just don't because we're lazy, and we accept that if we don't see something, that it means it's a square root. The other ones, we can't do that. We got to write it. So what times what times what is 1? 1. The next nice one would be 8. Next perfect cube. 2 times 2 times 2 is 8. 2 cubed is 8. The cube root of 8 is 2. Cube root of the next one would be 27. 3 cubed is 27. Cube root of 27 is 3. Next one is 64. 4 times 4 times 4 is 64. Cube root of 64 is 4. 125. 5 times 5 is 25, times 5 is 125, cube root of 125 is 5, and we'll just add one more here just to make it hard. 6 times 6 is 36, times 6 is 216, the cube root of 216 is 6. And then they keep going. We're going to use these today to help us simplify some answers, okay? So, using properties of radicals. Using properties of radicals. So we're going to be dealing with radical expressions, okay? And those are expressions that have radicals in them. So radical expressions, we're going to be simplifying them. The simplified form meets these conditions. Simplified form meets these conditions. So the first condition is, I'll read it the fancy way, and then we'll just kind of, no radicands have perfect nth powers as factors other than 1. Take out any perfect squares or whatever type of, now perfect squares are like these numbers. If you can get one of these out, then you should, okay? You cannot have fractions in your final answers, inside your final square roots. No fractions, and no radicals and denominators. So these are the things we're trying to get rid of. Okay, now we're going to look at some different properties that help us do that. So the first one is going to be the product property of square roots. Product property of squares. Now, product is when you multiply things. And so what it says is if you have multiple things inside being multiplied, you can break them up into separate square roots. You can do that. And then the square root of 9 is 3. Square root of 5. Can we take anything else out? Any perfect squares out of 5? Nope. So it stays inside and you multiply them back together. Now the 3 is on the outside. So we can break up radicals when it involves multiplication. You can't just break up radicals. There's a lot of times where you can't, but with multiplication, you can. So the rule in general is AB. So it's going to be the square root of A times the square root of B, where A and B are both greater than or equal to 0. They have to be positive or 0. You can't take square roots of negatives. So let's try some examples. Example 1. A, square root of 108. We're going to try and use this rule where we can break them up. So we're trying to look for these numbers, these perfect squares that we talked about up here that go into 108. And that can be kind of hard. If you're observant, you might be like, oh yeah, 36 goes in. That's 36 times 3. Right? And then we can break it up. Square root of 36 times square root of 3. And square root of 36 is 6 times the square root of 3. So we could do that. That's kind of hard. So I have another trick that I use where I do like a factor tree. Okay? I'll let you do it either way. So I'm going to do a factor tree. So I'm just going to think of what's the easiest number that comes to my head that I could break, that I could divide out of this. I'd say 2 because it's even. And half of 108 is 54. Then I can do another 2. Half of 54 is 27. And then I could do a 3 times 9. And then I could do a 3 times 3. So this is prime factorization where this is the factor tree and you're getting all the smallest numbers out. Now, if you're looking for square roots, they come from the same number multiplying each other. So the pair of 2's and the pair of 3's, that's a 4. The square root of 4 is 2. And for every pair, you're going to get one of those numbers on the outside. And anything left on the ends of the branches without a pair has to end up back inside. And then anything that you multiplied on anything that you brought out on the outside, you multiply back together. And anything left over on the inside, there might be multiple things, gets multiplied back together to give you your final answer. So that works. That to me seems like something I could probably pull off better than these big numbers. Now, sometimes the numbers are small enough that we could do it the other way. So here's another one, 9x cubed. So what we could do is we could say, okay, well, let's break this up into perfect squares. We have the square root of 9, the square root of x squared, and then a square root of just x, the first left over, because x cubed has an x squared in it, right? And then we say, okay, well, the square root of 9 is 3. And the square root of x squared is x. And then this one just stays, square root of x. That one we can't do anything with. Now, alternatively, you could take the factor tree approach. You say, okay, well, this is 3 times 3. And this is x times x times x. And every pair gives me a number out in front. Every pair gives me a number out in front. Anything without a pair stays inside. And we get the same answer. So it's up to you. I mean, you got to pick what works for you. Okay, C, the square root of 20x cubed. Now, in some of these, I probably wouldn't do the factor tree thing. I'd be like, oh, you know what? 20, I know a perfect square that goes in 24. And then there's a 5 left over, and I can't take anything out of 5. And then x cubed, I'd say, oh, well, there's an x squared in there I can take out, and then there's an x that's left over. So I'd say, okay, well, the square root of 4 is 2. I mean, we could rewrite this. Square root of 4 times 5 times x squared times x, and then we could write it all broken up. Square root of 4 times square root of 5 times square root of x squared times square root of x. And then square root of 4 is 2. Square root of x squared is x. All the stuff you take out should all go out in front. And then the square root of 5 and the square root of x, they go back inside into a single square root. Now, I could have, I think, jumped from here to here. If I just did these little breakdowns, like, oh, the 4 and the x squared, they come out, it's a 2 and an x, and then there's a 5x inside. So it's up to you. Okay. The next property is called the quotient property of square roots. Now, by the way, these properties work for any kind of roots, cube roots, whatever. Quotient property of square roots. Quotient's fancy word for division, fraction. So if you have the square root of a fraction like that, square root of 3/4, you can break it up in the square root of 3 over the square root of 4. So just like you can break up multiplication inside, you can break up division. And multiplication and division are related to each other. I'm just warning you, you cannot break them up if it's addition or subtraction. You can't do it. Now, this one right here, we say, oh, yeah, we know the square root of 4 is 2. Square root of 3, can't take anything else out. That's your final answer, okay? And so a generic way of writing this is the square root of a over the square root of b is going to be the same thing as the square root of a over the square root of b separately, where a is greater than or equal to 0. It's got to be positive 0. And b is greater than 0. B has to be positive. It can't be 0 because if it was, you'd have a 0 in the denominator and you get division by 0. That's undefined. Okay, so this is another rule we can use. Okay. So let's do a couple examples like that. So example 2, part A, square root of 15 over 64. Now, one of the rules we set up here to be done is that we can't have fractions inside. So that's what we're fixing right now. So the way to fix it is you break it up top and the bottom. And then square root of 64 is 8. Square root of 15, you can do a little factory, 3 times 5, no pairs, so everything stays inside. One of the other rules that is mentioned up here is that we can't have radicals in the denominator when we're done, which this worked out pretty nice. After this example, we're going to see ones that don't work out so nice. So we can break it up. Square root of 81 with the square root of x squared equals square root of 81 is 9. Square root of x squared is x. And that's your simplified answer. Okay. All right. Now, there's a slightly tougher problem with this issue. So we're going to look at, okay, rationalizing the denominator. So this is the third requirement that we mentioned above. Okay, rationalizing the denominator means get rid of radicals, roots, in the denominator. Okay, and so the technical name for that is called rationalizing the denominator. That's kind of like fixing it. And so I'm going to just jump into an example here and show you how it works. So if we have the square root of 5 over the square root of 3n, the problem here is we don't want a square root in the denominator when we're done. So how do we fix that? Well, we multiply by the exact same square root because we want to create a perfect square. If you do this, you're going to get the square root of 9n squared, which we could then break up. Square root of 9 is 3, square root of n squared is n, and now the denominator looks great. Now, can we just do that? Can we just multiply the bottom by whatever we want? yes, with fractions, you're allowed to multiply the bottom by whatever you want or the top as long as you do it to the top and the bottom. The reason that's allowed is because it's like we've multiplied by this new fraction, which really is just a 1, right? You can multiply things by 1 and it doesn't change their value, right? That's what we've done. By multiplying the top and bottom, this is the same idea we use for giving fractions least common denominators. You got to multiply the top and bottom. Now on the top, it's going to be square root of 15n. Square root of 5, square root of 3n. The rule that allows us to break up square roots for multiplication also allows us to bring them back together. Now, can we take anything out of 15n? 3 times 5 times n. No pairs, no perfect squares. So it just stays square root of 15n. Now, what some people are going to be tempted to do is they're going to be tempted to reduce these n's, but you can't reduce these because 1's inside a square root and 1 isn't. Same thing with the 3 and the 15. Can't reduce those. When you have some stuff inside square roots and some stuff out in a fraction, you can't reduce those. So this is it. This is the final answer. Do not get rid of the n's. Do not cancel them out. Let's do another example. 2 over the cube root of 9. Now this one's a cube root. Okay? If you just multiply by another cube root of 9, it's not going to work. Our goal is to get something inside that matches the kind of root it is. Like that's a square root. We needed things that were squared. Cube root, we need something that's cubed inside, right? And so hopefully you're thinking, okay, so we need to make this a perfect cube. Now, perfect cubes we listed on the front. One of them is 3 to the third is 27. Hopefully that comes up in your mind as a possibility. So you got to think, well, I got to multiply by the cube root of something here to make that gets multiplied with the 9 and gives me a 27. Well, that would be a 3. Whatever you do the bottom, you got to do the top. So on the top, we get 2 cube root 3. On the bottom, we get cube root 27, which we made that happen on purpose because we know that it gives us a nice answer on the bottom. Cube root of 27 is 3. Do not reduce those 3's. Okay? So that's called rationalizing the denominator. Now, there's a tougher situation. Same idea, but a little more complicated. So this is called rationalizing the denominator. And this time it's called using conjugates. So using conjugates, I'm going to show you what the issue is here. 7 over 2 minus root 3. Now, if we used, I'll show you how you might do this wrong. If we use the same trick that we did up here, people would be either tempted to multiply it by the same exact thing, top and bottom. Okay? And if you did that, you'd have to FOIL it. And you would get 2 times 2 is 4, minus 2 root 3, minus 2 root 3, plus square root of 9. I'm not going to do the top because I'm going to show you. On the bottom, this will give you a 3, and you would end up with 7 minus 4 square root of 3. Well, that didn't get rid of the square roots in the bottom. Some people might be tempted to, let me show you one other way you can mess it up. Oh, okay, let's just multiply by the cube root of 3, or the square root of 3. If you did that, you have to distribute it, and you get 2 cube root 3 minus, 2 square root 3 minus square root of 9, and that would give you 3. And you still didn't fix it. Some people might think, oh, we could cancel it. No, you can't do that. This would be your answer. Okay, so those ways don't work. So I just showed you how not to do it. Okay, so starting over, this is where the conjugate comes in. The conjugate is the same thing. So it's kind of like you're going to multiply the same thing with the opposite sign inside. So if this has a minus, this has a plus. If that has a plus, this has a minus in between them. This is called the conjugate. Whatever you do the bottom, you got to do the top of fraction. Okay, now on the top, we're going to distribute this. We're going to get 7 times 2 is 14, plus 7 times square root of 3 is 7 square root of 3. On the bottom, we do need to FOIL it. First, outer, 2 times square root of 3 is square root of 3. Inner, negative root 3 times 2 is minus 2 root 3. Negative root 3 times positive root 3 is minus square root of 9. Okay? Now, last time all the square roots kept hanging out even when we tried to get rid of them, but look at what happens here. The plus 2 root 3 and the minus 2 root 3, they cancel each other out. And there's in the square root of 9, it's 3. And so we end up cleaning the denominator up by multiplying by the conjugate. Now, our final answer, we don't need the 1. Right? Anything over 1 is just that thing. So it's not that the denominator is going to go away like it did this time. It's just that it's going to turn out clean. We're using this pattern back from when we would, this is the sum and difference pattern. This is like that a minus b times a plus b is a squared minus b squared. That was a shortcut. We call it difference of squares. There's sum and difference pattern. So we're using that to our advantage to get those extra middle terms that you would get here to go away. Okay. Operations with radicals. Now, operations are just like adding, subtracting, multiplying, dividing, okay? And so for adding and subtracting, radicals with the same index and radicand. Okay, so the index is the type of root, like square root, cube root. The radicand is what is inside the root, inside the radical, okay? So if they have the same kind of square root with the same thing inside, those are called like radicals. They're like each other, okay? So same root, same number inside. Then you can do stuff with those, adding, subtraction. Now, this idea, we use this idea from before. If you had 5x plus 2x, this is not going to be on this week's assignments, but this is just to help you understand it. If you had 5x's plus 2x's, you'd say these are like terms and that you have 7x's, right? You wouldn't say x squared, or you'd say 7x's. So same idea here. If you have 5 square root of 2 plus 2 square root of 2, so you have the same kind of square roots with the same number inside. It has to have the same number inside. If that's the case and you're adding and subtracting, you can combine these together. I have 5 of something and 2 of something. So I have 7 square root 2's. It's like I'm counting them. Okay? So let's try some examples using this. So example 5. Adding and subtracting radicals. Okay, so this is for addition and subtraction. So A, simplify. So I'm going to give you something like this. Square root of 5, parentheses, square root of 3, minus square root of 75. Now, one thing for any kind of simplifying problem in math is get rid of parentheses, distribute. So we're going to distribute this. Now, when we distribute this, we're going to use one of the rules that we talked about earlier. If you're multiplying a square root times another square root, you can just multiply their insides. Okay? Minus 5 times 75. Have fun with that. I'm going to show you idea, I think that would make this better. 5 times 5 is 25. Carry the 2. 5 times 7 is 35, and the 2 is 37. So that's 375. Okay. Now, these aren't like each other. Okay. So actually, this is, by the way, this is multiplying. I messed up. I'll show you the example. So at this point, these aren't like each other, like we were saying up here, so we can't combine them, but they might be in disguise. So you could do the factor tree thing over here. Now, by the way, the easiest pair to do right away is, how did we get 375? It was 5 times 75, right? In fact, I probably would have just left that square root of 5 times 75 inside, because I would know that I was probably going to be able to take something out. Now, do you know a perfect square that comes out of 75? 25. So you might just in your head recognize it and say, oh, I'm going to take the square root of 25. Or you could just keep going and say, oh, I got a pair of 5, so I'm going to take that out. So what we get now is square root of 15 minus the pair of 5s. You get a 5 out front. There's a 5 and a 3 left over inside, so that's 15. And these are like each other. So we have 1, positive 1 square root of 15 minus 5 square root of 15. So we have negative 4 square root of 15. Okay, now I jumped the gun. This is actually example 6. Example 5 was supposed to be adding and subtracting radicals, but I jumped to multiplying. So it's using the same idea. So let's say we had 5 square root of 7 plus square root of 11 minus 8 square root of 7. Now, the rule up here says it has to be the same kind of root with the same number inside. So these guys are like each other because of what's inside of them. And I can combine those together. 5 minus 8 is negative 3 square root of 7. The inside stays the same. This guy doesn't have anyone else to be combined with, and we can't simplify it. So plus square root of 11 stays the way it is. Okay, one more. 10 square root 5 plus square root 20. Now, at first glance, you might be like, well, that one's done. I can't take it. I can't combine these. Square root of 5 and square root of 20 aren't the same kind of radicals, but they might be after you simplify this one. So we can take a 4 out, right? And so this is the same thing as 10 square root of 5 plus 2 square root of 5. Take the square root of 4 out. The 5 stays inside. And so these are actually like each other. They're both certain number of square root of 5s. I got 10 square root of 5s plus 2 square root of 5s. I have a total of 12 square root of 5s. Okay. You're going to work on your monitoring progress classwork. And it starts on page 480. We're doing problems 1 through 6 all. They're at the bottoms of the pages. I would do it through the Student Dynamic ebook online, because there's little blue arrow buttons that you can play that will show you how to do the problem, and then also show you what the right answer is, so you can check your answers before you bother trying to work on the assignment for this one and end up doing them all wrong. It's good to figure it out. It's good to put some extra time in at the beginning and really make sure you get it. Make sure you check your answers before you move on and end up spending tons of time doing it all wrong, getting really good at doing it the wrong way. That's bad. It's hard to undo. So try these out.